In today's video, we're going to be going over calculus in 30 minutes. So the first topic you have in calculus is limits and continuity. And for this, you need to know what a limit is. So a limit tells you what happens to a function as the x value approaches a certain value. And it's notated like this right here. And the way you read this notation is the limit of f of x as x approaches a equals L. So keep in mind, the limit can and it cannot exist in certain functions and at certain values. So it only exists if the limiting value from the left side equals the limiting value from the right side. And I'll show you what that means in a second. So here, if you take this example, you have the graph of f of x equals x squared. And then if you want to find the limit at x as x approaches to 1, you have to approach the graph from the left side like this, and you see that it approaches 1. And then you have to go backwards from the other side, and you see that it also approaches 1. So that means that the limit does exist, and that the limit of f of x as x approaches 1 equals to 1. And now this brings me to my next point, which is continuity. So to put it in simple terms, a function is continuous if you can draw the whole thing without having to lift your pencil off the paper. Once you do, then that means that function is discontinuous. So I'll give you an example, and it also ties back to limits. So the limit doesn't have to do with the value of the function, it's more so what the function approaches. So if you look at this example, we have f of x equals x minus 1 whole squared divided by x minus 1. And the domain is that x cannot be equals to 1. And if you try to evaluate the limit at x equals 1, you have to approach it from the left side to see that it approaches 0. And then you have to approach it from the right side, and you see that it also approaches 0. So the limit does exist even though at that value, your function is undefined. And this is the first type of discontinuity. It's called point discontinuity. As you can see here, the limit from the left side is equal to 0, which is also equal to the limit from the right side. And then you have another example, which is a piecewise function where it's equal to x minus 1 when x is less than 1, and then it's equal to 2 plus the square root of x minus 1 when x is greater than or equal to 1. So now if you look at this graph, if you approach it from the left side, it approaches 0. But if you go back and trace it from the right side, it approaches 4, positive 4. That makes the limiting value from the left side and the right side not equal to each other. And this means that the limit, in this case, does not exist. This is the second type of discontinuity. It's called jump discontinuity. And the third type is asymptote discontinuity. This is when you basically have an asymptote in your function. And the most prominent case in this would be f of x equals 1 over x. So as you can see, you have a vertical asymptote, and you also have a horizontal asymptote, and this makes your function discontinuous. And now we move on to the next topic, which is first principle definition of derivatives. So first of all, you would need to know what a derivative function is. And a derivative function is basically a function that tells you how much your original function is changing by at a particular second or at a particular instant. So let's take this example where f of x equals to x squared. And then you have the formula, which is f prime x, this little dash is pronounced as prime, and it says that f prime x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So the first step you would need to do is identify your f of x and f of x plus h. And for you to get f of x plus h, you just take your original function and plug in x plus h instead of x at every x you have. And once you simplify this, it looks somewhat like this because it's a perfect square. So f of x plus h is going to be x squared plus 2xh plus h squared. And now you can go ahead and plug it into the formula, and it's going to go as follows. F prime x is going to be the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared. So if you look at these two are like terms, so they actually cancel out, and it brings us to this part, which is going to be 2xh plus h squared divided by h, while you still have your limit. And now you can't evaluate your limit at this particular instant, because if you evaluate your limit, that means you would have to plug in 0, and you'd have to divide by 0, and that would give you a mathematical error. So you have to find a way to get rid of the h's first. And once your original terms cancel out, you will always end up with terms that all have h's instead of them. So you can go ahead and factor one out like I did here, and then it cancels out, and it becomes, you have terms that have x's, and you have terms that have h's, and you have terms that have x's and h's. But now at this step, you can go ahead and evaluate the limit, which means plugging in h as 0, which just simplifies your derivative function to 2x. So this is how you do it with this formula, but there's actually a shortcut that is a lot more useful than having to do this all the time, which brings me to my next topic, which is the power rule. So the power rule says that if you have a function of f of x equals x to the power of n, that means the derivative is going to be nx to the power of n minus 1, which basically means you take the exponent, you put it to the front, and then you minus 1 from it. And I'm going to show you how this works in a second. So let's go back to the example we just did, which is x squared. So if we follow this, then it's going to, you take the exponent, put it to the front, and then you minus 1, which is going to be 2x to the power of 2 minus 1, 2x, which is just 2x, once you simplify it. And if you see, this is what we got here. And then if you look at a different example, we'll take x cubed. You take the exponent, put it to the front, minus 1, which is going to give you 3x squared. And keep in mind, you would have to multiply it by whatever the coefficient is of your variable. So you take the exponent, put it to the front, and now it's 5 minus 2, and then you minus 1 from the, you minus 1 from it, and now you're left with 10x. And now we're moving on to the product rule. So the product rule states that if you have a function, px, which is the multiple of two different functions, f of x and g of x, then p prime x would be the derivative of f of x multiplied by g of x, and the derivative of g of x multiplied by f of x. So it looks like p prime x equals to f prime x gx plus g prime x fx. So let's take an example where px equals 6x squared. F of x and g of x are 3x and 2x respectively. So what I like to do is I like to lay them on top of each other like this, just so it gives me a clearer view. And then you can get f of x and its derivative, and g of x and its derivative. And then you can go ahead and crisscross them and multiply them. And now you're just left with p prime x equals to 3x times 2 plus 2x times 3, which once you simplify it is just 6x plus 6x, which gives you 12x. And if you noticed, you would get the same answer if you use the power rule instead, which would just be bringing the exponent to the front, so it's going to be 6 multiplied by 2, and then x to the power of negative 1 is just going to give you 12x. So if you use the power rule, it gives you the same answer, but the product rule is more convenient in certain situations, and the power rule is more convenient with certain situations. Same thing applies for the quotient rule. So the quotient rule states that if you have a function, h of x, and it's f of x divided by g of x, then the derivative of h of x, h prime x, is going to be f prime x gx minus g prime x fx over gx squared. So let's take this function as an example where h of x is x over x plus 1. And now we do the same thing. We just lay them out on top of each other, and we get each function's derivative, and we crisscross them. But keep in mind, with this one, you have to be mindful of what you put first, because the product rule dealt with addition, and as you know, addition is commutative. You can change the order and it doesn't impact your answer, but that's not the case with subtraction. So you have to make sure that you multiply f prime x gx first, and then you subtract g prime x fx from it. And then if you follow the formula, you just get this, and then once you simplify it out, it's going to be x plus 1 minus x over x plus 1 whole squared. And then as you can see, these two cancel out, and you're just left with 1 over x plus 1 squared. And the last of the rules that you have to know is chain rule. So chain rule is mainly used for composite functions, in which you might have heard the expression a function inside of a function before. So the way to know if your function is a composite function is you try to substitute something inside for a variable and see if it becomes one function. So in this case, you have x squared minus 5 to the power, all to the power of 7. And in this case, we can try to say let x squared minus 5 be u. So now you've substituted it, and now you can say that your function is u to the power of 7. But u is a function of itself. So you can get the derivative for the outer function and then multiply it by the derivative of the inner function, which is basically where this comes from. So you can still apply the power rule, and in this case it would be 7u to the power of 6, but you would have to multiply it by the derivative of your inner function, which is u. And now I'll show you how that works. So if you start taking the derivative, it's going to be 7. You bring this down, and then you subtract 1 from it. So it's going to be 7 x squared minus 5 to the power of 6, because you multiply it by 1. And then you go to your inner function, and you take the derivative of that, which is just going to be 2x minus 1. So it's going to be 2x. And then the derivative of 5 is just 0, which cancels out. And once you simplify this term, you're left with 14x multiplied by x squared minus 5 all to the power of 6, and that's going to be your derivative for this function right here. Now let's take a different example where f of x equals to 3 divided by 9 minus x squared. So then you can go ahead and actually change this to become a negative exponent, because that's easier to work with considering the power rule that we almost always use. And now I'll go ahead and take this just to see if it's a composite function. I'll go and try to substitute this to be 9 minus x squared equals u. And now we've changed my function from this to 3u to the power of negative 1. So now I know I can apply chain rule, and I'm doing so right here. And when you multiply it out, it's going to be negative 3, u minus 1, so it's going to be negative 2. And then you multiply it by the inner function, which is u prime. And then if you simplify this, it's going to be negative 3 times 9 minus x squared to the power of negative 2 multiplied by 2x, multiplied by negative 2x. And then these negatives cancel out, and it becomes 6x over 9 minus x squared to the power of 2. And that's going to be your f prime x. The next topic we're going to go through is curve sketching. So for curve sketching, there's an algorithm that you should follow, and I'm going to show you that algorithm right now. So in this question, it says, sketch the graph of this function, f of x equals x cubed minus 6x squared minus 9x plus 54. So the first step would be to find the domain and the range of that function. And since it's a cubic function, it's going to look somewhat like this, something like this. And we know that it extends along the x-axis and the y-axis. So the domain and the range are both x belongs to R and y belongs to R, respectively, with no restriction. The second step would be to find the zeros. So in this case, through trial and error, I was able to use synthetic division to get one of the zeros, which was 3. And I plugged it in, and I came out with x squared minus 3x minus 18. If you don't know how to use synthetic division, I'm going to show you right now. So then you lay out the terms with their coefficients 1, negative 6, negative 9, 54. And then you divide by a certain number, which is going to be on your side here. And then you start with 0. And it's going to be 1 plus 0, which is going to give you 1. And then you multiply it by 3, and it's going to give you positive 3. You add them, and then it gives you negative 3. You multiply them, and it gives you negative 9. You add these two, and it gives you negative 18. And then you multiply these two, and it gives you negative 54 with positive 54. So then they cancel out, and you're left with 0. If you're left with 0, that means that this is one of the zeros that you have for this function. And these are going to be the coefficients for your new function, which is going to be 1 degree less. So I went ahead and simplified this to x minus 3 multiplied by x squared minus 3x minus 18. And then I went ahead and I factored this expression, and I got x minus 6, x plus 3. And then from this, I was able to get my 3 zeros for this graph, which were x equals 3, x equals negative 3, and x equals 6. And now it's time to do something called the first derivative test, where the first derivative test, you basically get the first derivative for a function, and then you set it to 0, and then you solve for the x values. And the x values give you the local minima right here, and maxima and minima, sorry. And then that's possible because at these points right here, the slope is 0. So this is where it gives you the maximum and minimum value. You would know their x coordinates. So that's what I did right here. I went and I got the first derivative, which was 3, put it to the front, minus 1, 3x squared, 2 multiplied by negative 6 minus 1 minus 12x, and then the derivative of negative 9x is just negative 9. And then I set it to 0 and I started solving, and then once I got to this point, I could use the quadratic formula and get my 2x coordinates, which were x1 equals 4.64 and x2 equals negative 0.65. And now I went ahead and I made a table just so I can have like a better idea of what to envision. And then this table, I separated it into intervals. So you take the interval before, you have 0.65. One second. You have 0.65 and you have negative 0.65 and you have 4.64. So you take the interval before, add it, between them, add it, and then after. And I'll show you why in a second. So once you do that, take the interval before, add it, between them, add it, after. And then you want to see if the interval is positive or negative. And I'll show you why. Since the derivative function gives us the slope, at a certain point, if it's positive, that means your graph is increasing. And if it's negative, that means your graph is decreasing. And that's what's going to help us. So if we plug in a value here, we get a positive value. So we know from negative infinity till this point, our graph is increasing. And then once we get to 0.65, we know that it's either going to be a maxima or a minima. But we can't decide that yet. We have to check the interval after, which is between negative 0.65 and 4.64. And once we plug in a value for that, we get a negative value, which means our graph is decreasing. So if we go from an increase to a decrease, and then we have a point with 0 slope, then this makes it a maximum. And we can go ahead and plug in the x value back into our original function, which is this, to find out the actual coordinate, which is 57.04. And then we do the same thing with the next one. We plug in a value that is more than 4.64, and then we find out that it's positive, and therefore it has to be increasing. So if you go from a decrease to a stationary point, and then back to an increase, that means that this point was a minimum. And then you would take the x coordinate, and you would plug it into the original equation to find out what your actual point is. And this just gives us a general idea of what the graph is going to look like, as well as some key points for us to plot it. And then the second derivative test is, once we get our function, the first derivative, we have to get the second derivative, which gives us something called the point of inflection if we set it to 0 and solve. So the point of inflection is basically when you have a change in the upwards trajectory in the upwards/downwards trajectory of your graph. So if you have something like this, then the point where it stops being an upwards curve and becomes a downward curve, that would be your point of inflection. And that would help us get a more accurate graph. So then once we do this, getting the second derivative is just as simple as differentiating the first derivative, and its notation is 2 dashes. So now it's called f double prime x. And then once we solve for it, we get that x equals 2, and then we can go ahead, since we know that x equals 2 is the point of inflection, we can plug it back into the original equation and get that the point of inflection is now 2 and 20. And now I'm going to show you how you actually sketch the graph using the data that we just got. So the first thing to do would be to plot the zeros, which are positive 3, negative 3, and positive 6. And then the next thing we want to keep in mind is that if you look back at our original function, The leading coefficient is 1, so it's positive. And since it's an odd degree function, that means it's going to go from the third quadrant to the first quadrant. And we know that it's a cubic function, which means its general shape is going to look something like this. And now we can go ahead and plot our local maxima and local minima. So our local maximum is at negative 0.65, which is somewhere here, at 57, which is going to be somewhere here. So I'm going to go ahead and plot that. And it's going to be around right here. And that's going to be my maximum. And then my minimum would be at 4.64 at negative 17.04. So I need to go to 4, and 4.64 is somewhere around here. I need to go all the way down to negative 17.04, which is going to be approximately around here. And then if we can go back, we know that from the interval where x is less than negative 0.65, our graph is increasing. So if we go to 0.65, which is going to be our local maximum here, we know that our graph is going to be increasing. So it's going to look something like this. And then it's going to start decreasing from 0.65 till negative 0.65 to 4.64, which means it's going to keep decreasing now, and it's going to go down, and then it's going to go back up, since we know it's an odd degree polynomial, and it's going to start in this quadrant and finish in this quadrant, and it's going to go somewhere like this. So this is as accurate of a sketch you can get your graph. Of course, your graph can look neater. I'm going to try to draw that in a second, a lot neater. But this is what the graph should look like. And it's going to look something like this. And this is the graph of f of x equals to x cubed minus 6x squared minus 9x plus 54. And for the last topic we have in today's video, it's optimization. So optimization is basically when you take a function and then you try to find the minimum or the maximum to get something more efficient. It could range from maximizing the profit for a company when you have its model to something like this, where you have to minimize the dimensions to minimize the cost. So let's go ahead and read the question. It says, a cylindrical shaped tin can must have a capacity of 1,000 centimeters cubed. So we know that our volume is going to be 1,000 centimeters cubed. Determine the dimensions that require the minimum amount of tin in the can. So we're going to find the minimum. The smallest, according to the marketing department, the smallest can that the market will accept has a diameter of 6. So if that's the smallest, that means the radius has to be bigger than or equal to 3. And a height of 4 centimeters. And that means that the height has to be greater than or equal to 4. So we can go ahead and take the two equations that we have, which is going to be volume equals pi r squared h and the surface area. So the reason we need two equations is because we have two variables and we need to isolate one of them and substitute it into the other equation. So we go from two variables to just one variable. And I'll show you how to do that. So since we know that our volume is 1,000, we can go ahead and substitute 1,000 instead of volume. Then we have 1,000 equals pi r squared h. And I'm going to choose to isolate for h because r has a squared on it, and we can avoid a lot of unnecessary headaches if we just isolate for h. So that's what I'm going to do. I'm going to divide by pi r squared on both sides, and it's going to give us h equals 1,000 by pi r squared. And now since we have a value for h, we can go back and plug it into this equation, and we're left with 2 pi r squared plus 2 pi r, and then this is the substituted value for h. And once we simplify that, it's going to give us 2 pi r squared plus 2,000 pi r over pi r squared. The pi cancels with the pi, the r cancels out with one of the r's. So you're left with 2 pi r squared plus 2000 over r. And now we can bring this up and give it a negative exponent just so it's easier for us to apply the power rule over here. So since we have an actual model, we can go ahead and get the derivative for us to be able to get the minimum. And if you look at this is a quadratic function. So it's going to look like this. And since the leading coefficient is positive, because it's positive 2, it's only going to have a minimum, and that's what we're looking for. So if you go and get the derivative by applying the power rule, it's going to be 2 times 2, 4, minus 1. So it's going to be 4 pi r minus negative 1 times 2000 is going to give us negative 2000 minus 1 is going to be r to the power of negative 2, and the r just comes back down. And now the next step would be for us to solve for 0 to get the minimum. And once we do that, we just bring this to the other side, and we have 4 pi r equals 2000 by r squared. And then using cross multiplication, we know that 4 pi r times r squared is going to be equal to 2000 times 1. And that's what we're left with. 4 pi r cubed equals 2000. Now, the next thing to do would be to isolate for r. And now we can divide by 4 pi on both sides. And this just gives us r cubed equals to 159.1 centimeters. And if we take the cube root for both of these sides, we're left with r equals 5.42. And now if we go here, back to our original equation, we know that h equals to 1000 over pi r squared. And now since we have a value for r, we can plug it in and solve for h to see what's the minimum height that will give us an area of, what would be the minimum height that would give us a volume of 1000 when paired with this value for the radius. And when we plug it in, we find out that our height is 10.84 centimeters. So then if we go back to the restrictions that we had on our domain, we can see that the radius is bigger than our restriction. So that means our radius value is valid. And our height is also bigger than 4. So this part is also valid. So this is going to be the end of this video. I hope you guys enjoyed this. And if you found this helpful, please let me know in the comments.